Well, the first condition that comes to our mind is this, to explain to a layman why y bar is a good thing. So when I am measuring this beta using our scale y, of course we are making mistakes, so it's quite likely that we are making mistakes, but whenever we make a mistake, it could be either overshooting it or undershooting it. Now the idea is sometimes we will be overshooting it, sometimes we will be undershooting it, and on an average these things should cancel out. If you think that you are always overshooting it, then of course taking the average is not a good idea. For example, if you take the time shown by various peoples on their watches at a certain instant and take the average of that to estimate the true time, that will be a bad way of doing it, because most people will keep their watches slightly faster. I'm not talking about mobile watches because those are just exact, but generally if you use wrist watches or the clocks at home, they're usually more of them are running faster than slower. So fast clocks are usually preferred by people than slow clocks. So there, taking simple average will not be a wise thing. Or suppose you suddenly figure out that the scale that you are using is by mistake not marked from 0 but marked from 1. In that case, in all these cases, the error will be approximately around 1. You have made at least 1 centimeter error. In that case also, you will not use simple average. So when you suggest that simple average is a good way of combining all the numbers, you are tacitly assuming that you are as much likely to overshoot as you are to undershoot. That is why if you take lots of such random measurements, average them out, they are likely to cancel each other out. That is just from our layman's viewpoint. Now, you can write this as a more statistical sounding condition by saying that epsilon i's are on an average is 0. It might overshoot, it might undershoot, but on an average they should be 0. Expected value of epsilon I is equal to 0. So when you are suggesting that let's take average, you are tacitly making that assumption. If that assumption is not valid, you will not be willing to use average. Now that's not the only assumption. Suppose I am going to measure this 10 times. Now I am a bit too lazy. I have measured it only 5 times. And then I ask my friend to take the remaining 5 measurements. Now my friend is a rather skilled engineer and he uses not just ordinary scale but a slide caliper. So he carefully opens this slide calipers and then measures this and gets some very precise measurements. So we have got 5 measurements which are taken by the ordinary scale and 5 measurements that are done by a slide caliper. So if I average my 5 and his 5, I will get most likely 2 different numbers. Now, should I just take the average of these 2? That is not reasonable because this one is just an ordinary scale. So I had to do lots of eye estimation and gives me result closest up to a millimeter, and even then I have to do a lot of squinting of my eye. But this one is fitted with a vernier scale. It can go on up to 0.01 centimeter, that is 1/10 of a millimeter. So this is more precise. In this case, taking simple average does not look like the best thing to do. So if I have my average and my friend's average, I would rather prefer to do a weighted average where I give more weight to the measurement taken using the higher precision instrument and less weight to the measurement taken by the lower precision instrument. I am not going to discuss how you choose those weights, but the main thing is that when we are using simple average, we are making the tacit assumption that all the measurements are of the same level of precision. Statistically, that means I am assuming variance of epsilon i's are all same. I do not know what that variance is, some sigma square positive number. Of course, if sigma square is equal to 0, that means I am just in a precise measurement setup. That is not feasible in practice. So I am allowing that the sigma square is unknown, but they are all having same sigma square. This is referred to as the homoscedastic setup. Okay, that's not all. We put yet another assumption. Suppose I am using just my scale and I'll be measuring all the things myself. So I know that expectation of epsilon I is 0, variance is the same, but as I said, I am lazy. So when you ask me to do this, what I do is, well, you have asked me to take 10 measurements. Okay, I will take one measurement very carefully. And then when I see no one is looking, I will just repeat the same measurement 9 times and say, well, I measured them 10 times and these are all the things. So you see, I am not violating my assumptions because the first time I measured epsilon 1, that expectation was 0, and epsilon 2 to epsilon 9, they are also the same thing, so their expectation is also 0. Similarly, variance of epsilon 1, whatever it was, remains constant because epsilon 2 is same as epsilon 1. But will you think that taking average of these 10 numbers is really going to add to the precision? Now remember, when we take average, we have this idea that I have taken 10 measurements and average of them, so the entire thing is more precise than the original thing. But here, the average of all these so-called 10 measurements, which all happen to be the same number, is the same number itself. But will you put any greater faith in this average number than on the first number? No, because this so-called average is not an average at all. It is just the first number itself. So our intuition that taking average of 10 numbers will give you a more reliable figure does not work in this case. So we are assuming that all these measurements is shedding some fresh light on this. So all the errors are at least uncorrelated. Epsilon i's are uncorrelated. Otherwise, taking repeated measurement is not really a good idea. For example, I know of certain students, when I was in higher secondary, I had some lab assistants or friends who were working with lab partners rather, who had this bad habit of doing back calculating at every step. So the moment they will see one measurement, they will work out by back calculation what the value was supposed to be according to physics theory, and if they have overshot it in the very next measurement, they will write down something which will undershoot it so that the average remains the same. So they are basically making all these observations correlated, negatively correlated in their case, such that the average is indeed the value that is given in the textbook. But obviously such an experiment is meaningless because even though you have taken say 100 measurements, since they are correlated, they merely reflect what you believe the value should be and not what nature says the value should be. So when we are using simple average meaningfully, we are tacitly making these three sets of conditions. The first is on the mean, that all the errors must have zero mean. Secondly, they must have the same variance, unknown, that is fine, but same variance. And the last thing is that they are uncorrelated, or later we will make it more stronger, they are independent, but for the time being, we say that they are uncorrelated. And these are the most simple set of conditions that we can think of to make any such measurement scenario meaningful. There are situations where it will be violated, like using various instruments of multiple precision, etc. But this will be our starting point, and these are called the Gauss-Markov setup. So whenever we say we have a linear model in the Gauss-Markov setup, we mean that the epsilon satisfies this condition. So y equal to x beta plus epsilon vector, and its components satisfy these conditions. We saw that y bar, the simple mean, has some nice properties under this Gauss-Markov setup. We shall see now in the next video that least square estimators in general enjoy certain nice properties under these assumptions.